Hello everyone, welcome back to my channel. So in this video we are going to learn about gray code. Okay, so we are going to learn about gray code. If you are first time to my channel, please consider subscribing and hit the bell icon to get video notifications from my channel. Right, so gray code is an example of non-weighted code. Okay, so gray code is an example of non-weighted code only. Right, so we will first know how to write the gray code, and then we'll discuss about the properties. Suppose if you have 1 bit, so 1 bit you can divide it as 0 and 1. Okay, 0 in one category and 1 in one category. Suppose if you want to write the 2-bit gray code, so this is 1-bit gray code. So if you want to write 2-bit gray code, so 2-bit gray code will have 4 combinations. So for first 2 combinations you have to write zeros, and for second 2 combinations as MSB you have to write ones. Okay, and then for the remaining bits you have to write these 2 numbers 0, 1. And for the lower bits, you have to write the mirror image of this. Right, so when you write the mirror image of this, it will be in reverse order, so 1 and 0. Okay, so mirror image, if you see, so if the mirror image will be in this direction, then it's if the image is in this direction, then its mirror image will be in this direction. So you have to write all the values in this direction, that is 1 and 0. So I have written 1 and 0 like this. Okay, so this is called as mirror image property. Similarly, if you want to write 3-bit gray code, so 3-bit gray code will have 8 combinations, right? So for the first 4 combinations it is 0 0 0 0 MSB bit, and it is 1 1 1 1. And the remaining 2 bits, first of all you have to write in order all these 4 bits, that is 0 0 0 1, so 1 1 and 1 0. And for the remaining you have to write in this order, that is mirror image of this. So mirror image of this is 1 0 1 1 0 1 and 0 0. Okay, so this is how we can write the 3-bit gray code. Understood? So 0 1 as it is, so 0 0 for a 2-bit combination, for 2 bits you will have 4 combinations, so 0 0 in the first top. Okay, so divide it into 2 halves, so 1 1 you have to write, so MSB bit is 0 0 for the first half and 1 1 for the second half. Next you have to write these 2 bits in order, so 0 1 as it is and in order I have written, and for the bottom side you have to write its corresponding mirror image. So mirror image will goes like this, right? So 1 to 0, so I have written 1 and 0, so this 1 1 mirror image, and 0 here 0 here, right? And similarly 0 0 0 0 and 1 1 1 1 MSB bit, first of all you have to write these MSB bits, right? So remaining bits is obtained from here, right? So 0 0 0 1 1 1 1 0, so 0 0 0 1 1 1 1 0 as it is I have written. And for the bottom side you have to write the mirror image, so 1 0 here, so this is the mirror image, and this is the mirror image, and this is the mirror image. Okay, similarly if you want to write for 4-bit, for 4-bit how many combinations will be there? 16 combinations will be there. So top 8 combinations will have MSB bit as 0, so 0 0 0 0 0 0 0 0. And similarly bottom you have 8 combinations. Okay, so these are the combinations. Similarly, so for the top remaining bits will be these combinations, so these 8 combinations, so 0 0 0 0 0 1. So in order you have to write 0 1 1 0 1 0 1 1 0, right? 1 1 then 1 0 1 and then 1 0 0, and then it is mirror image, so 1 0 0 1 0 1 1 1 and then 110 0 1 0 0 111, sorry 011 001 000. So that is, this is the gray code for decimal number 0. So this is the decimal value. So for decimal 0, this is the gray code. For decimal 1, this is the gray code. This is gray code for decimal 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so this is the decimal code for 0 to 15. Okay, so you can remember like this how to write, right? So is in easy form I have told you, because it exhibits one property. Okay, so in my next slide I'll explain you how to find this using conversion concept also. Okay, so from binary to gray code and gray to binary conversion, you can also find this directly. Okay, right. So gray code is called as unit distance code. Gray code is also called as unit distance code. Okay, so why it is called as unit distance code is consecutive numbers differ in only one position. Okay, so 1 bit position, of course, 1 bit position. So if you see 3 and 4, so what is the representation of 3? 0 0 1 0. And what, so for 3 it is 0 0 1 0, and for 4 consecutive numbers it is 0 1 1 0. So they differ in only 1 bit position. Remaining 3 bits, they are same. Not only 3 and 4, you can take for 10 and 11 also. What is 10 representation in gray code? It is 4 ones. And for what is 11 representation? It is 1110. So it is differing in only 1 position. So successive numbers differs only in 1 position. That is why gray code is called as unit distance code. This is one more point which you have to remember. Okay, and gray code is also called as cyclic code. Gray code is also called as cyclic code. Okay, gray code is also called as cyclic code, or it is also called as reflected code. Reflective is different. Reflective code is also called self-complementing code. Okay, so we have discussed about that in the previous video. But this is reflected code because it has the property of reflective property or mirror image property. So just now we have discussed. So mirror image property. Okay, so what is that reflected code is? For n least significant bits, codes for 2 power n to 2 power n plus 1 minus 1 or mirror images of 0 to 2 power n minus 1. Okay, so suppose for n is equal to 3, so 3 least significant bits. Okay, I'm talking about 4-bit gray code. For 3 n least significant bits, that is n is equal to 3 if you take. So for 3 least significant bits, the codes for 2 power n is 2 power 3 to 2 power n plus 1, that is 2 power 4 minus 1, that is 16 minus 1, which is equal to 15. So the codes for 8 to 15 are mirror images from 0 to 2 power n, that is 2 power n minus 1 is 7. So for 0 to 7, so n least significant bits means 3 least significant bits, as we have seen already. Okay, so I am writing in theoretical form. So the 3 least significant bits from 0 to 7 are mirror images of the 3 least significant bits from 8 to 15. Okay, so this is what we have written, right? So using that property only we have written this 4-bit gray code. Okay, so these are mirror images for least three least significant bits of 0 to 7. So 0 to 7 means these values, or mirror images for 8 to 15. Okay, so these are all the properties of gray code. Okay, so I hope you have understood. So gray code is also called as non-weighted code, unit distance code, cyclic code, reflected code, because it has the reflective property. And gray code, very important point, and very important point used asked many times in many competitive exams is application of gray code. Gray code is used in Karnaugh map. Okay, so gray codes are used in K maps. So we'll discuss about this K maps in our upcoming videos, right? So until then, remember that the application of gray code is it is used in K map simplification. Okay, so that is the thing. Because of this unit distance property only we are using this in K maps. Okay, so let me take one more slide. I'll explain you gray to binary and binary to gray conversion, right? So next we'll see gray to binary conversion. Okay, so gray to binary conversion, and also binary to gray conversion, that is binary code to gray code conversion. Okay, so these two are very important concepts, gray to binary and binary to gray, right? So in order to convert this we need the help of XOR gate, right? So I'll explain you XOR gate in my next videos. So until then you just remember this: 0 XOR with 0 is 0, 0 XOR with 1 is 1, 1 XOR with 0 is 1, and 1 XOR with 1 is 0. So you just remember these four. Okay, so I'll explain you later in my logic gates concept about exclusive OR gate. Okay, so this operation, this representation is called as XOR representation, and this XOR representation is used in the conversion of gray to binary and binary to gray. Okay, you just remember this, right? So for time being just remember this, we will discuss this clearly later. Okay, so gray to binary conversion, right? So gray to binary, so you are given with gray code. Okay, so you have to convert that into binary. Okay, so convert that into binary. So you are given with gray code, so let that gray code, 4-bit gray code I am taking, let that 4 bits be G1, G2, okay, G1, G2, G3 and G4. Okay, G1, G2, G3 and G4. So its corresponding binary is given by, so MSB bit you have to take as it is. So G1 is equal to B1, so MSB bits doesn't change. Okay, so once you got the MSB bit, you have to XOR it with the next gray bit. The obtained binary bit is XORed with the gray bit, so that you will get B2. Similarly, you have to XOR B2 with G3, so that you will get B3. Similarly, XOR these two, you will get B4. Okay, so this is the binary number, right? Similarly, binary to gray conversion, that means you are given with binary and you have to convert that into gray code. You have to convert that into gray code. So if you are given with binary, I am taking that binary number as B1, B2, B3 and B4. Okay, so conversion will be like this. So B1 is equal to G1, so MSB bits will be same, right? So next G2 will be obtained by XOR operation of B1 and B2, so this will be G2. Next XOR operation will be G3. So these two XOR operation will be G4. So this is your gray code. Okay, so we'll take an example. Suppose 8. I am taking the example of 8. Okay, so we first of all I will do binary to gray conversion, and then I'll convert gray to binary also with this same example. Likewise, you can apply it to any number. Okay, so binary of 8, binary, this is gray code of 8, right? This is gray code of 8. So binary of 8 is represented by, we know that one in 4 bits it is represented as 1000. Okay, so now binary we have obtained. So B1 is 1, B2 is 0, B3 is 0, and B4 is also 0. Right. So if you want to convert that into gray, so we'll see whether we are getting the same result or not. So we have to write the same value for G1, right? So same value B1 is equal to G1, right? So these two XOR operation, one XOR with 0. So 1 XOR with 0 is 1, so resultant is 1. So if you do XOR operation with B1 and B2, you will get the value G2. So G2 is equal to B1 XOR with B2. Similarly, what is G3? G3 is equal to B2 XOR with B3. Similarly, what is G4? G4 is B3 XOR with B4. Okay, so these two XOR operation. So 0 XOR with 0 is 0, and 0 XOR with 0 is again 0. So this is the corresponding gray code. Is it we are obtaining same or not? So 1100, same gray code we have obtained. Okay, so you can remember by using this reflected property as we have seen in the previous slide, or you can remember by using this conversion concept also. Okay, so now we'll perform gray to binary using for the same example. So gray code is 1100. I'm taking this gray code and now converting it to binary. So we'll see whether we'll get 1000 or not. Okay, using this concept. So G1 is equal to B1. So G1 is equal to B1. So 1 only as it is. Next, so how we'll get B2? B2 is B1 XOR with G2. So these two you have to XOR. Right? So 1 XOR with 1. So 1 XOR with 1 is 0. So you'll get 0 here. Next, these two XOR operation. 0 XOR with 0 is 0 again. Next, 0 XOR with 0 is again 0. So you're getting 1000. So if you have taken this gray code 1100, you are getting corresponding binary as 1000. And if you are taking the binary as 100, you are getting the gray code as 1100. Okay, so this is how we can convert gray code into binary code or binary code into gray code. Okay, so you can extend this to any number of bits. Suppose if you have 6 bits in binary, right? So say 6 bits in binary, B1, B2, B3, B4, B5 and B6 are there. Correspondingly you'll get 6 gray code bits. So B1 is equal to G1. So these two XOR, you'll get G2. These two if you XOR gay, so you'll get G3. These two if you XOR, you'll get G4. These two if you will XOR, you'll get G5. These two if you XOR, then you'll get G6. Okay, so you can extend this concept of conversion to any number of bits. Okay, so this is about gray code.